Good morning, everybody. I'm Galatsopoulos, and I'm going to talk to you about my Midgard GPU architecture. So we'll dive a bit into the internals of the GPU, and I'll also try to focus on the benefits that these architecture features give you when you're developing your mobile graphics applications. So let's have, first of all, a quick look into the hardware evolution of Mali GPUs. As you can see in our roadmap over here, we have split it in two parts, in the energy-efficient GPUs and in the cost-efficient GPUs. And we have identified from a quite early stage that the mobile market is quite big and there are quite different requirements according to the device that is being used. So the high-end devices are mainly focusing on energy efficiency because they want to deliver the highest performance, and they're usually thermal or power constrained. While the lower-end devices, mid to low-end range, they are very cost sensitive. So performance, of course, does matter again, but the silicon area is one key feature that needs to be optimized so that they can become affordable. So on the energy-efficient roadmap, we have started with Mali T604, which is the first GLES 3.0 and full-profile OpenCL capable GPU. We have moved forward to Mali T624 with 50% performance uplift and support for ASTC. Then T628, which is extending the scalability from 4 to 8 shader cores. And finally, Mali T760, which is taking scalability even further to 16 shader cores, and also introducing lots of SOC-level energy efficiency features, which we will focus on later in this presentation. And on the cost-efficient roadmap, we have started with Mali 400 GPUs, which is one of the most successful ARM GPUs out there, delivering the best performance density, so highest performance for a given area for GLES 2 applications. Then we have moved to Mali 450, which is doubling the number of cores and potentially doubling performance as well. And then we are going again to the Midgard architecture, so T622, which is the first cost-efficient GPU supporting GLES 3.1 and OpenCL full profile. And last product in the cost-efficient generation is Mali T720, which has been optimized for area and low time to market as well. So we'll go through the architecture on a high level for T760. So as you can see on the top, we have the inter-core task manager, which is the block that is distributing tasks, taking them from the Mali application through the Mali driver and submitting them to the shader cores. For T760, you can have up to 16 shader cores that will be working in parallel. Then we have the advanced tiling unit, which is making sure that we have an efficient mapping of all the geometry primitives to tiles. We have the memory management unit, which is doing the standard transformation between virtual and physical address space. And of course, the appropriate number of L2 cache and an ACE-Lite interconnect, which is giving you I/O coherency. So let's have a further look into the graphics pipeline. I won't go into too much detail. I just want to stress out the basic flows. So in an immediate mode rendering GPU, which is very typical for the desktop world, you'll have geometry submitted by the application through the driver, and you have one very long pipeline from start to end, where you're processing the vertices, you're shading them, and then you're going to rasterization, fragment shader, and finally blending the pixels from that particular primitive within the whole frame buffer scene. So this may sound like a quite simple and easy, architecture, but it has a number of problems, especially in a mobile environment where you have certain restrictions. And the biggest one is the high memory bandwidth that you need, as you can see here for blending, but also in the other stages when you're having big primitives that are starting from one part of the frame buffer and ending up to the to the other end, or you have a big chunk of frame buffer within a single primitive, you cannot have very good efficient use of caches. So you're having lots of cache misses, and you have to go back and forth to external memory, which is costing you performance and power. So in the mobile world, we are using tile mode rendering. Most of the mobile GPUs are using that. So we are effectively splitting the vertex and pixel shading. And in this way, you can do the pixel shading in small tiles and have very good and efficient use of the caches, avoid all the external bandwidth, and save yourself power and better performance. So the only overhead in this case is that after doing the vertex shading, you have to store the pre-processed geometry in external memory, along with the triangle list, one per tile, which is going to be provided to the next stage of processing, in pixel processing, in order to do the process on a tile-per-tile basis, and in order to make sure that you will only read the relevant geometry for this tile. And then at the final stage of the pixel processing, we have the tile buffer, which is an internal SoC memory, and you only go to external memory after you have finished processing the complete scene within this tile. So a bit of data flow so that you can understand the software-hardware interaction. So the application is submitting draw calls to the driver, which is then creating the job descriptors in shared memory, as well as the input data, which can be both vertex and pixel data, all the shaders, all the textures, everything you need to put together your scene. So the job manager within the GPU is picking up the descriptors and is splitting up the tasks to finer grained jobs that can be distributed in parallel across multiple shader cores. And they won't have any dependencies in between them, so that you can efficiently process all of them in parallel. Then the shader cores are picking up the input data. They're doing some processing. They may have to store intermediate data, like frame buffer objects or render to texture data. And then on the final stage, they will pick this up and produce the final frame buffer to be displayed on the system display. So diving a bit further into the tri-pipe architecture that all Midgard GPUs have. So the tri-pipe thread execution is the core of the shader core that is doing most of the processing. And as you can see, there are two paths with going and feeding into this core, depending on the type of tasks that you have to process. So the first one, compute thread creator, is actually used to generate the compute tasks as well as the vertex processing tasks, while the other flow is being used for pixel processing. So as we said, we have split the processing between these two, vertex and pixel. So the fragment processing path will pick up the data structures from the tiler. It will go through the triangle setup unit, so it will calculate the equations of each primitive, submit them to the rasterizer in order to convert primitives into pixels and find out which are the pixels that intersect with each primitive. Then we have the early Z part of the processing, which is effectively eliminating all the hidden pixels. So any object that is behind some other object, some other opaque object in the scene, is being processed by the early Z, and we are making sure that we are not going to feed this workload within the tri-pipe. So tri-pipe is doing most of the hard work in terms of rendering the scene. And then we have the final late Z pass to make sure we have the correct ordering between objects, because this can change within the tri-pipe execution as the shader has this ability to change the ordering between objects. And we have the final blender, which is feeding to the tile buffer. So once we have finished processing all the primitives within a tile, then we are submitting the tile buffer to external frame buffer in memory, and go fetch the next one, and so on. So here is how the core of the try pipe looks like. As you can see, there are 3 different types of blocks that are needed to process the scene. Each one of these has different depth in terms of the pipeline. So we have arithmetic units, which are doing all the classic arithmetic processing. We have a load store unit and varying unit, as well as a texturing unit. So all of these blocks working together, they're making sure that you're having a high efficiency and high graphics throughput. You can have many threads running simultaneously, and the fact that you're separating the processing in these 3 units means that you can have more threads in flight, and you can hide all latency issues, because if you're having external dependencies on a thread, you can pass on to the next one, and you maintain high throughput through your GPU. So in terms of scalability, we have introduced scalability in 2 ways. So apart from the obvious number of shader cores that can change, and for Mali T760, they vary from 1 to 8 shader cores. As you can see here, within each shader core, you can have 1 or 2 ALUs. So for the cost-efficient part of our roadmap, we are restricting to 1 ALU, because you don't need to process high complex content, and it's all about processing UIs and low complexity applications in this case, which are not compute limited. While for our high-end roadmap, for T760, for example, you can have up to 16 shader cores, each of which has 2 ALUs, which is making it more efficient for high complex compute tasks. Again, 64-bit support is something that we have introduced with Midgard architecture. So all T6 XX GPUs and all the newer GPUs after that, T7XX, are supporting 64 bits. And it is quite important, because we had this wake-up call that 32 bits may not be enough to have the full address space required for high-end devices, and we are practically reaching the limits of high-end devices in terms of the address space that they need to have. So Midgard GPUs are offering both 64-bit address space as well as 64-bit compute processing, and this is also very important for OpenCL, because full profile OpenCL does require 64-bit precision, and by supporting that, you can easily take the desktop compute applications and port them to your mobile device. And many scientific algorithms are using this 64-bit format. So in order to support APIs like GL4.x, DirectX 11, CUDA, or OpenCL, you need to have 64-bit precision. So some further use cases for 64-bit is for processing pointers to addresses. So you need to have 64-bit integers in this case. Also for high dynamic range graphics processing, and for cool effects like the bokeh effect over here, where you can have this nice blurry lighting that is making the application looking so much nicer, and also for some area variance shadow maps. 64-bit precision is really mandatory. And most importantly, even if you can accept some compromise in your image quality, when you're processing compute tasks, there are applications that precision does really matter, and they couldn't work otherwise. Memory bandwidth is also another area where we have tried to optimize our GPUs for, because this is a key limiting factor in terms of your power budget. So accesses to external memory do consume power, and also are affecting performance if you're in a bandwidth-limited system. So in T600 family, we have introduced a number of optimizations compared to Mali 400. So in terms of textures, we have introduced improved texture compression. We have also introduced a concept called transaction elimination, which we will look into detail. And also with hierarchical tiling, we have also minimized the bandwidth consumed by the tiling process. So ASTC is the new texture compression format that we have introduced. And as you can see on this matrix over there, all the blue dots are all the different configurations that you can have with ASTC. So you can choose your bitrate and you can choose your color format, and you have all that many options that you can get the best compromise between image quality and pixel throughput. While other texture compression formats like ETC will just provide you what the red dots indicate, so much more restricted options in terms of what bitrate and what color formats you can use. Moving forward to transaction elimination, this is a concept introduced by T600 family. So we have identified that in most applications, consecutive frames look a lot like each other. So we are splitting them in tiles, and for each new frame, we are comparing it against the previous one. And for the part of the scene that is identical, on a tile-per-tile basis, we are not writing out the final frame buffer. We're just passing a pointer to the driver saying that this particular tile has been static, so you can reuse the same tile from the previous frame. And in this case, we are saving lots of write bandwidth because we don't have to rewrite the redundant part of the scene. So for static frames, you can have 100% reduction of write-out bandwidth. But even in high dynamic games, we have seen that maybe 20% or more of the tiles are still remaining static, and you can have good bandwidth savings from that. Another example is Angry Birds. So you can see 2 consecutive frames over here, going back and forth. This slight move will obviously change the content in many tiles, but you can see that 28% of them are going to remain static, and we have good bandwidth elimination because of that. Also on T760, apart from reusing all the mentioned above features, we have introduced a number of new bandwidth-saving features like AFBC, or ARM frame buffer compression, and smart composition. And what I would like to stress here is that all of these features can work together, complementing one another and delivering you very high bandwidth efficiency in your application. So it's not a matter of choosing one or the other. All of them can work together and provide you the best possible result. So for this composition workload, for example, on the GPU, you can have the input surfaces coded by AFBC, and you can apply the smart composition concept, which we'll look into, and have good bandwidth saving, along with the other 2 features that can be used in parallel. So AFBC is a frame buffer compression algorithm. It's a lossless algorithm, so you don't have to make any compromises in terms of quality in order to get reduced bandwidth. And the nice thing about it is that it can be used in your whole SoC. So it's not just a GPU feature. We have introduced AFBC in our video codec in Mali V500 and also in our display processor in DP500. And we're also providing AFBC as a standalone block that can be introduced in any third-party IPs that are processing images like ISPs or any other type of processor. And therefore, you can have your whole SoC working efficiently by passing compressed buffers from one IP to the other. So on the bottom right-hand side, you can see the bandwidth savings that we can achieve by AFBC. So when you're compressing a frame by AFBC, you can have a typical 50% reduction, even quite higher than that in some use cases. But when you're having the overall application, obviously just a fraction of it will be bandwidth related to frames. So for example, T-Rex is having this very low compression rate just because it's having lots of vertex complexity, and only a small proportion of the bandwidth is attributed to buffers, which can be frame buffers that can be compressed. While other more balanced benchmarks like Manhattan or even real applications like Angry Bird are having a better, vertex to pixel complexity ratio, and you can achieve much better compression for the overall application. So smart composition is another very interesting feature that is picking up on the concept of transaction elimination and extending this even further. So with transaction elimination, you would have the bandwidth saving only after you have done the whole processing of the scene. Then you would go and diff it against the previous frame. What smart composition is allowing you to do is identify the similarities within two consecutive frames before the frame is even being processed. And in this way, you're not only saving write bandwidth, but you're saving read bandwidth of all the input surfaces that would have to be read. And you're also saving computation processing, which will not take place for the part of the scene that has been identified as static. So as a summary, Midgard architecture is a highly scalable architecture, both in terms of shader cores, as well as in terms of computation processing, and the ratio of compute to texturing can be variable, providing the best solution according to the target applications for that particular GPU. We have introduced a number of bandwidth saving techniques, which are saving you both power and also improving performance in bandwidth limited systems like ASTC, transaction elimination, smart composition, and AFBC, as well as tiler and interconnect optimizations. And we are also supporting all the major graphics APIs like OpenGLES 3.1, OpenCL, and Windows DirectX. So that was all. Any questions about any topics I have covered?